Welcome to Structural Analysis 2 video series. Unit number 4, Stiffness Method. Lecture outline: numerical on sinking of a support in a beam. So this is the second part of a previous problem. So we gone through the problem statement. We calculated the degree of kinematic indeterminacy. Then also we assign the coordinate direction to the unknown displacement theta b and theta c in the anticlockwise direction. After that, we've gone through the external force acting in the direction of a coordinate assigned, and there is no any external moment acting in the direction of coordinate theta b and theta c. That means the AD1 and AD2 both are the 0. After calculating that whether the external moment acting or not, then we move toward the ADL. So ADL means force in the coordinate direction of a restrained structure. So we keep each span restrained. First we considered the span AB and we calculated the fixed end moment, and then due to the sinking of a support, whatever the moment produced at B that we calculated, so that gives us a moment or force acting in the coordinate direction when the structure or when the span AB is restrained, and from that we calculate the force acting in the direction of a theta B for by considering span AB. After that, we consider the next span BC, and for that also we calculate the whether there is a moment acting in the coordinate direction when our coordinate direction is theta b and theta c. So we calculated the moment acting in the coordinate direction, and after that whatever the total moment acting, that we sum up, and that moment come out minus 84.17 and minus 45. After this calculation, we move ahead and we then calculated the or we form the stiffness matrix. For that, we apply the unit rotation along the coordinate direction theta b in anticlockwise direction. So at B, we apply the unit rotation theta b is equal to 1, and same rotation will observed for span BA because that joint is a rigid joint. And then we sum up these two rotation which is occurred on the both span BA plus BC, and we know that moment is 4 EI by L. So we put the value of moment of inertia and length of respect to span. Then we have 2 EI. Then we know that the half moment carry at the far end. When we are applying a rotation at B, the far end we keep as a fix, and the far end that means the location of a second coordinate. So what moment observed at the second coordinate when we applying the unit rotation at the first coordinate, that we noted as a 2 EI by 4, and that come out 0.5 EI. Then we move toward the in the calculation of second column of a matrix, and for that we apply the unit rotation along the theta c is equal to 1. So we will get that unit rotation as a 4 EI by L by putting the value of that respect to span. We have EI value for S22. So this is the second coordinate and this one is the first coordinate. Here we apply the unit rotation at second coordinate, and due to that second rotation at second coordinate, what happened at coordinate location 1 and what happened at coordinate location 2, that we calculate, and that nothing but the second column of a stiffness matrix. Then we form the, after the calculation, we form the stiffness matrix. Okay, so now this is the second part of our previous problem. So let's move toward the now second part. After calculating the coordinate of a stiffness matrix, we develop the or construct the superposition equation of equilibrium of forces. So AD is equal to ADL plus S into D. So putting the value, AD means AD1 and AD2, ADL means ADL1 and ADL2, and stiffness matrix is a 2 by 2 because our degree of freedom are 2. D1 and D2 are the unknown, theta B and theta C. So ADL1 is a minus 84.17, ADL2 is minus 45, S11 is a 2, S12 is 0.5, S21 is 0.5 and S22 is 1. D1 is equal to theta B and D2 is equal to theta C. So taking this 84.417 toward the left hand side, it become plus 84.17 is equal to EI 2 into theta B plus 0.5 into theta C, and for second 0.5 into theta B plus 1 into theta C. By taking this EI outside for the both equation and taking 45 minus 45 toward the left hand side, become plus 45. Solving these two equations, we have theta B is equal to 35.24 divided by EI and D2 is equal to theta C is equal to 27.38 EI. After knowing this value, then we have to calculate end moment by using slope deflection equation. So let's apply the slope deflection equation for span AB. So MAB is equal to MFAB plus 4EI by L into theta B, theta A plus 2EI by L into theta B plus minus 6EI by L square into delta. So MAB is equal to MFAB, we know from the previous calculation, 106.67. Now theta A is 0 because A is a fixed support, so theta no rotation at A, so theta A is 0 plus 2EI, moment of inertia of AB is 2I, so 2E into 2I divided by 8, 8 is a span of AB into theta B plus 7.5. We know the moment created due to the delta already calculated, and we, after putting the value of theta B as 35.24 by EI, we have MAB 131.79 kN meter. Now apply the slope deflection equation at B for span BA. So MBA is equal to MF for BA plus 4EI by L into theta B plus 2EI by L into theta A plus minus 6EI by L square into delta. We know MF for BA from previous calculation minus 106.67, 4 into E into 2I divided by 8 into theta B plus 0, again the A is a fixed support, so theta A will be a 0 plus moment due to the sinking of a support is plus 7.5 as calculated earlier. Now by solving, by putting the value of theta B as 35.24 by EI, we having moment at B MBA is equal to minus 63.93 kN meter. So we having a moment, end moment create at A and B. Now let's find out end moment create at B and C by considering span BC. Again apply the slope deflection equation. MBC is equal to MFBC plus 4 EI by L into theta B plus 2 EI by L into theta C plus minus 6 EI by L square into delta. Now putting the value theta B and theta C, theta B is 35.24 by EI and theta C 27.38 by EI. Now we know the friction moment MFBC 30 and I moment of inertia is I and span BC span is 4 meter, and also 6 EI by L square into delta as calculated earlier is minus 15. So by solving we have MBC is equal to 63.93 kilonewton meter. Now apply the slope deflection equation for end C. So MCB is equal to MFCB plus 4 EI by L into theta C plus 2 EI by L into theta B plus minus 6 EI by L square into delta. So putting the value MCB is equal to minus 30 plus 4 EI by 4 into 27.38 EI plus 2 EI by 4 into 35.24 EI minus 15. So we have MCB is equal to 0, and that is proof that our end C end is simply supported, so end moment at C will be 0, and that is calculated mathematically, that come out to be 0. Now after drawing the end moment, now let draw the bending moment and shear force diagram. So let first draw the bending moment diagram. Now this one is a superimposed bending moment diagram. So first consider span AB as a simply supported and find out free bending moment diagram for 20 kN per meter UDL. So it is WL square by 8. So W is 20 and L is 8 meter. So we will get 160 kN meter. So this is UDL. So draw the parabola. Now for span BC, consider simply supported span and find out free bending moment for 60 kN point load acting at mid span. So it is WL by 4. So by putting the value 60, W as a 60 and L by 4, we will get 60 kN meter moment, and it will be in triangular fashion. Now draw the bending moment diagram for the end moment. Now our end moment at A is 131.79 kN meter, and it is in a anti-clockwise sense, positive value. So you have to rotate about A in anti-clockwise sense. So after cutting the member AB, that arrow coming up, so you have to show up. Now at B, the end moment MBA is coming out to negative. That means you have to rotate about B in a clockwise sense. So rotate at B in a clockwise sense. After one rotation, the arrow coming up, the value is 63.93 to show there, and last value is 0 and the moment is 0. So we will get the bending moment diagram. You just join with the line bending moment diagram for the end moment. Now the portion which is not overlap, that you have to show with the hatch. So this is your bending moment diagram. Now let do the calculation for the shear force. So let consider first loading diagram and then draw the FBD of each span AB and BC. So AB having a 20 kN per meter UDL. So 20 into 8 divided by 2, we will get reaction at A and B 80 kN. Now for span BC, load is acting 60 kN divided by 2, we will get reaction at B and C 30 kN. Now show the end moment for each span. So at A there is an end moment in anti-clockwise direction. Positive sign is there, and its value is 131.76. Make it correct, anti-clockwise 131.79, and at B it is in a minus sign, so clockwise direction 63.93. Now these moments are not balanced because they are not having the same magnitude. So we have to find out the reaction due to the unbalanced moment. So take a difference between these two. 131.79 minus 63.93 divided by span. We are having a value of 8.483. So this value you have to show first below the maximum moment. So maximum moment is 131.79. So below that you show the 8.483. Now arrow direction you have to mark. Now for that you have to look at the far end, and far end moment is 63.93 and it is in a clockwise direction. So this moment is lesser than the 131.79. So this reaction should be in upward direction. So when it rotates, it will get added into the 63.93 and it will form the clockwise moment. So once this arrow is shown in upward direction, then look toward the far end and same magnitude force you have to mark there 8.483 and that you have to mark opposite to the first one in a downward direction. Okay, so it will form the couple to make this 131.79 moment in a balanced condition. Now let's look toward the second span BC. So at B end there is a anticlockwise moment 63.93 and at far end there is no any moment. So it creates unbalanced situation. So to overcome that, the member will create couple in opposite direction. So that direction will be in a clockwise sense. So to maintain that clockwise moment, you have to find out the reaction first. So 63.93 divided by span 4, so is equal to 15.98 kilonewton force. Now first you have to locate that force below the maximum moment. Now there is a question of arrow. So whether arrow should be up or down. So that arrow should be up. Why up? We need at the far end clockwise moment. So to get the clockwise moment, this should be up, so it will rotate and it will give me clockwise moment. Now at the far end you have to take same magnitude force 15.98 and that force you have to show opposite to the first. Now first is up, so the far end force you have to show down and its magnitude is 15.98. Once these forces are marked, you have to do the summation. So first force is 80 kilonewton up plus 8.483, we having 88.48. Then at B, for BA span 80 kilonewton minus 8.483, we will get 71.52 kilonewton upward. Now for BC span at B 30 kilonewton up plus 15.98 kilonewton up, we having 45.98 kilonewton up. Now at C 30 kilonewton up minus 15.98 kilonewton, we having plus 14.02 kilonewton up. So total reaction at B is equal to 117.5 kilonewton by doing addition of 71.52 plus 45.98. So now we know the reaction at each support A, B and C. Now from this, let's draw the shear force diagram. So at A, there is a reaction in upward direction 88.48 kilonewton. So it will move up. Now there is a UDL, so 20 into 8. So that value you have to reduce from the 88.48. So plus 88.48 minus 20 into 8. So we having minus 71.52 plus this reaction minus 71.52 plus 117.5 kilonewton, we having plus 45.98. For UDL you have to mark line, incline line. Then after getting 45.98 there is no any load, so straight line up to 60. So plus 60, sorry, minus 60, you will get minus 14.02. So there is no any force in between this 60 kilonewton and reaction at C. So there is a straight line, and the reaction is minus after minus 14.02 plus 14.02 upward, you will get a 0 shear force at C. So this is your shear force diagram. Okay, so in this way we calculate the bending moment and shear force diagram. Okay, so let's stop here. Thank you.